Let's see the 21st question. In a general metric space, closed and bounded does not always imply compact. Because in RK, closed and bounded always implies compact, but in general metric space, it does not imply. Second, that is 22nd question. If P is a point in the metric space X and P does not belongs to K, where K is compact, then there exists. P is a point in metric space and P does not belongs to K. K is compact, then there exists. So option disjoint neighborhood of P and K. Yes, that's the option. Disjoint neighborhood of P and K. So every KSL is compact. So differentiation, contradiction only, induction property. Every KSL is compact uses which technique? So I think so option A is right. Let's see the next. For a subset E of a metric space is if every infinite subset has a limit point in E, then E is compact. In every infinite subset has a limit point in E, E is compact. Which mathematician's name is associated with the property that bounded infinite set has limit point? Weierstrass. If G is equal to union VP, where each VP is a neighborhood, then G is. VP is a neighborhood, union of open. I think so, open. Yes. Compactness is considered an dash property because it does not depend upon the surrounding space. Compactness is considered an dash property because it doesn't depend upon the surrounding space. I think so. Extrinsic? No. It is intrinsic property. If E is a subset of Rk and E is not bounded. If it is not bounded, then we can say so it cannot be compact. Think so. Yes. E is not in Rk, it should be closed and bounded. So if it is not bounded means we can say so it is not compact. Then if F subset of K subset of X and F is closed relative to X, then I can say F is compact. Let me check that. Yes, F is compact. The distance between 2 points X and Y in Rk is given by distance between in Rk. So maybe this. Yes. Summation xi minus yi the whole square the whole power 1 by 2. So let's see the next question. That is 31st question. In the proof that every KSL I is compact, we assume I is not covered by any finite subcollection of an open cover. What is the immediate next step in the bisection argument? I is not covered by any finite collection, then what is the immediate next step? Subdivide I into 2k smaller cells by bisecting the sides. Yes. If a set E is closed relative to Y and Y is closed relative to X, then which of the following is true about E in X? So E is closed in X. Yes, closed is transitive. So E is closed in Y and Y is closed in X, then we can say according to transitive property E is closed in X. The set of all rational numbers in the closed interval 0, 1 is not compact. Rational numbers in the closed interval 0, 1 is not compact because it has, sorry, I think so it is, no, actually it is not closed subset of R1 because compact set in Rk must be closed. Since the set does not contain irrational limit points, so it is failed to be compact. So in R1, the question here 0, 1, no? So it is not compact, it is not closed. Okay, it is not closed subset of R1. Right. A collection of sets G alpha is defined as an open cover if E subset of union G alpha and E G alpha is open. Yes. So an open cover must contains of open set whose union contains the entire set E. Next, theorem 2.34, that is took from Walter Rudin, Principles of Mathematical Analysis. There you can see that established that if E is a compact subset of a metric space, then the complement of is open. I think so, open, because E is compact. Compact is closed and bounded. So let's see, the complement of E is open. Yes. And the next one, a closed interval AB in R1 satisfies which of the following descriptions? AB in R1. It's in one cell and compact or correct. Let me see. It's partially true, but both the description, that is one cell and as a compact set, are correct. Option C is correct because it is given here closed. Also, we know that R1 is a one cell. So from this both we can say it is closed as well as one cell. Right, and the next one, if K is a compact set and every sequence Pn in K has a subsequence. If it has subsequence, then it is converges to a point in K. Yes. By the property of sequential compactness, we can say K has a subsequence that converges to the point. The property of the set E being open relative to Y if is a characterization that depends on the relationship between E and the subspace Y in which it is contained. That is given in theorem 2.30 that E is equal to Y intersection G for some open G in the large space X. Ninth, that is 39th question. If E is compact, which of the following must be true? About its diameter. E is compact set. If it is compact set, then the diameter is finite. Because compact sets are bounded, so maximum distance between any 2 points is in the set. So diameter is finite. Then the last question 40. In the context of metric space topology, the empty set is closed, compact, open. Empty set is closed, compact, open. I think so all the below. Yes, empty set satisfies